Okay, thank you very much. Sorry for my incompetence with the Zoom. Okay, so as my talk indicates, I'll be talking about a universal property of the scale of counting of operators and states and conformal field theories at large spin. This talk is based on this paper that we put out in December with Harsh Anand, Nathan Benjamin, Vipul Kumar, Jyotirmoy Mukherjee, Shrideep Pal, and Ashikur Rahman. And I've given references to other relevant papers here. I will refer through the talk to the numbers and maybe indicate the institutions in which the papers were written. I will also make brief reference to an upcoming paper by Zohar Kumar Gotki and collaborators. Okay. So this is the table of contents. It's an ambitious table of contents, and let's see how far we go. Let's start with the introduction. As everyone here knows, conformal field theories are interesting theoretical structures. And as everyone here knows, the spectrum of operators in a conformal field theory is perhaps one of the most basic observables that characterize the conformal field theory. Now, conformal field theories have many nice things about them. One really nice thing is the state operator map. The state operator map tells us that there's a one-to-one correspondence between local operators in the theory and states of the theory when you quantize it on a sphere. So although our paper deals with all dimensions greater than 2, in this talk, just for clarity, I will stick to the special case of conformal field theories in D equals 4. Okay, so in this case, the state operator map tells us that there's a one-to-one map between operators of the theory and states of the theory on S when you quantize the theory on S3. And as you know, the map tells you that the scaling dimension of operators maps to the energy of the state, and the spins of operators map to the angular momentum of the state when the state is put on this S3. So the object of study from my point of view will be this partition function, the partition function that counts states in the conformal field theory when you put it on an S3. But also by virtue of the state operator map, that also equally well counts operators in the theory graded with respect to scaling dimensions and spin. Okay, and the notation I will use through this talk is the following. My partition function will be trace e to the power minus beta h is the energy, minus plus beta omega 1 J1 plus beta omega 2 J2. J1 and J2 are the two angular momenta in the two orthogonal two planes. You can imagine S3 is being embedded in R4, and R4 has two orthogonal two planes. These are the angular momenta J1 and J2. And I will sometimes use this alternative notation. I will sometimes group together things in a different way. So I will sometimes write the same partition function as e to the power minus beta tau minus nu1 J1 minus nu2 J2, where tau is a quantity I'm going to call the twist. It's e minus J1 minus J2. And nu1 and nu2 are what I will sometimes call reduced angular velocities. Omega 1 and omega 2 I will call angular velocities through the talk. And if you don't know why that's an appropriate name, we will discover as we move along in this talk. Okay. Now this partition function is a trace, and for a minute, let's approach it from a formal point of view and ask the following question. For what real values of beta, omega 1 and omega 2 is this partition function well defined? Well, a moment's thought will tell you that the partition function is not well defined if beta is less than 0. And that's simply because e to the power minus, the spectrum of the Hamiltonian is unbounded from above at fixed J1 and J2. So this trace simply diverges if beta is negative because of the unbounded spectrum at fixed J1 and J2. Okay. Now, so this partition function is well defined for beta greater than 0, but it's not well defined for beta less than 0. And this formal statement is, of course, very physically meaningful. Beta greater than 0 is positive temperature. Beta less than 0 is negative temperature. Partition function is not well defined for negative temperature. And the boundary between these two, which is beta equals 0, has a very familiar physical interpretation. Beta is the inverse temperature. So beta goes to 0 from positive side. Is temperature going to infinity from positive side? Okay. And so the boundary of well-definedness in terms of temperature is the high temperature limit. So that's a sort of interesting place from this point of view, but of course from many other points of view. And, in general, there's a general one should expect that if something diverges at a certain value, the approach to this divergence is an interesting thing. Okay. So part of my talk will focus, in the review part, will focus on this high temperature limit. However, there is a second thing that we will also study in this talk, which is the new part. And the second thing we will study in this talk is the following. Recent studies of gray galaxies in ADS space have drawn attention to the fact that there is a second such divergence, very much like the divergence as beta goes to zero. And this divergence is the following. Where this partition function is divergent when omega becomes larger than 1. Okay? Even when the temperature is fixed and positive. And the reason for this is very simple. Look, this quantity J1 here, let's consider a particular derivative, a derivative that is in the holomorphic direction in one of these two planes we talked about before. That derivative carries h equals 1 and J1 equals 1, and therefore carries twist equals 0. So adding more and more such derivatives are not suppressed by e to the power minus beta tau because these derivatives don't carry twist. And if omega is greater than 1, they are enhanced by this new 1 times J1. Okay, so just like you get a divergence when temperature is negative, you get a divergence when omega is greater than 1. Or actually, more precisely, when the modulus of omega is greater than 1. Okay, so the high temperature divergence is a familiar divergence in the study of all theories. This omega goes to 1 divergence, perhaps less familiar. And investigation of this divergence, what we can say about conformal field theories as omega is taken to 1 is the main topic of this talk. Okay, but as I said, before getting to the new stuff, what I say will make more sense when you counterpose it with old stuff. So let me start with the old stuff. As you know, the old stuff is describing the first bound approach to divergence that we talked about, namely the high temperature limit, the limit beta goes to 0. The limit beta goes to 0 is very familiar. Consider any conformal field theory on a unit S3. Length scales associated with motions in that conformal field theory are set by the length scale of the S3. In the limit the temperature goes to infinity, on the other hand, there's a second length scale, namely 1 over T. And this is roughly the length scale of collisions, the length scale of local equilibration. Because this length scale is much smaller than the length scale of the sphere, one expects on general grounds that any interesting dynamics in a conformal field theory in the high temperature limit on S3 is described by solutions to the equations of hydrodynamics. Now, we're interested not in any old solution to the equations of hydrodynamics. There are plenty of very interesting solutions to that fascinating theory, but we're interested in computing thermal equilibrium. So for that purpose, the only solutions that are of interest to us are the solutions that describe equilibrium. Now, hydrodynamics has this magnificent property. It follows by considerations of the entropy current from considerations that tell you that entropy can only be produced and never destroyed, even locally. That every equilibrium solution of hydrodynamics has zero value of the shear, where shear is just symmetric derivative of the velocity field. Okay, the velocity, so the basic equations of motion of hydrodynamics are a local velocity and local temperature. Okay, the shear is a symmetric derivative of the velocity field with the trace removed. Okay, now there are plenty of components of the shear, much more than the number of variables of hydrodynamics. There are d variables in hydrodynamics, but roughly d into d plus 1 by 2, well, minus 1, the equations from sigma mu nu equals 0. So this is plenty of equations for fewer variables. So solutions to the equation sigma mu nu equals 0 are very constrained. And in fact, one can prove that the only such solutions, when you put this theory on a manifold M, the only such solutions are velocity fields which are proportional to conformal killing vectors of the manifold M. Okay? So we've just managed to solve for all equilibrium solutions of hydrodynamics. The only such solutions are velocities where the velocity is some conformal killing vector. Of course, on S3 times time, the conformal killing vectors are famous. They're the generators of the conformal algebra, SO4, 2. And up to SO4, 2 rotations, all such velocity fields can be put in this form. Okay? So this is del t plus omega 1 del phi 1 plus omega 2 del phi 2. This is the velocity field that describes a fluid in rigid rotations, moving the phi 1 direction, the phi 2 direction. Okay, well, rigidly. Okay, and gamma is the Lorentz contraction factor that you have to multiply this killing vector by to make sure that it's normalized. Okay, So that to make sure that u squared is equal to -1, so it's a legal velocity field. Okay, and then one can easily check that this velocity field solves the fluid equations if and only if the temperature field takes the form T naught times gamma of theta. So now we've completely solved for the solution of hydrodynamics. Once we have the solution, we can evaluate its stress tensor, therefore we can evaluate its energy, we can evaluate its angular momentum, we can evaluate its entropy current, and therefore its entropy. And from all of that, reconstruct the thermodynamics of the solution. And we find, after Legendre transforming to go to canonical frame, that this thermodynamics takes the following form. The log of the partition function is C prime times T cube over 1 minus omega 1 squared into 1 minus omega 2 squared, where C prime is a constant that cannot be determined on general grounds. It's the constant that appears the equation of state of a conformal field theory, which, as you know, tells you that locally log z is C prime times T cube. C prime is that constant up to some proportionality factor. And that's dynamically determined. In n equals 4 Yang-Mills, it differs between weak coupling and strong coupling by this famous factor of 3/4. This you cannot determine on general grounds. But we have determined a lot on general grounds. We've determined the general form of the partition function for every conformal field theory on general grounds. This result was first presented in our paper in 2007. It's 20 years old. It's recently been reviewed, and the analogy with the Cardi formula in 2-dimension emphasized in this Caltech paper much more recently. Okay, now one thing that I want to emphasize that will be important as we go along is that this partition function is positive. Log z is positive for omega less than 1, blows up at omega equals 1, and becomes negative, so sort of unphysical, because remember, partition function is like a trace, for omega greater than 1. Okay, and you can ask, what's the deal? What's the deal from hydrodynamics? What's special about omega equals 1? Now remember, we're looking at a unit sphere. So if you look at the equators of the unit sphere, you see that omega represents the speed of the fluid. And omega equals 1 is special because it's the speed of light on the equator of the sphere, or one of the equators of the sphere. And so the fact that omega cannot go faster than 1, larger than 1, is just, Einstein. It's the statement that nothing moves faster than the speed of light. You try to send something faster than the speed of light, you get junk. Okay? Note that this partition function is well defined all the way up to omega equals 1 because there are no speed limits in physics. Lower than that is the speed of light. Now, all these nearly trivial sounding observations have a sort of interesting something, which we, at least only entered my head when we wrote this paper 3-4 months ago, though it could have 20 years ago. And it goes as follows. Look, let's, as an exercise, said omega, just for simplicity, said omega 1 equals omega 2 equals omega. So omega 1 equals omega 2, and we'll call the value omega. Now, as we've emphasized, our partition function is well defined for mod omega less than 1. Okay, so we conclude, you see, a partition function is only well defined if we're computing a trace of something that is bounded from below, or bounded from below if we do e to the power minus that charge. And so we conclude that this charge, E minus omega into J1 minus J2, must be bounded from below for all mod omega less than 1. Now, what guarantees this? At first sight, you might think this is guaranteed by the unitarity bound in conformal field theories. But then you pull up the unitarity bounds, which has been worked out, of course, long ago. And you find that in the case J1 equals J2, which is sort of relevant for omega 1 equals omega 2, you find E is greater than or equal to J plus 1. That's the unitarity bound if J1 equals J2 is equal to J. But if J1 is equal to J, J2 is equal to J, at omega equals 1, we wanted tau to be greater than or equal to 2J. Okay? So unitarity goes half the way to what we want, to explaining what hydrodynamics is telling us, but only half the way. So this suggests that actually there's a better bound than simple unitarity tells you, that actually it should be that E is greater than or equal to J1 plus J2, so that the tau is bounded from 0. And this puzzled us for a while, and then we discovered that, we realized that Clay Cordova and friends had conjectured, but almost proved, an annex, a bound using the Annex principles of the Annex, that, consider 3-point rather than 2-point functions, used unitarity, used positivity of the stress tensor, and demonstrated that slightly more non-trivial considerations than what we normally use for conformal field theory unitarity, at least strongly suggest. I mean, they proved for small representations and conjectured for all representations that E is greater than equal to J1 plus J2. Okay, so the stronger than unitarity bound of Cordova and friends has a really simple, cool interpretation from hydrodynamics. It's simply a reflection of the fact that there's no barrier in speed below the speed of light. Okay, the upcoming paper by the Stony Brook group has another perspective using similar, not too different logic, another perspective on this, and which you guys will hear about it. Okay, now that's one derivation of what we get at high temperatures. Okay, and to my taste, is a very physical derivation. But, you know, to certain kind of physicists, it feels a bit, what is equilibration? What is time scale? Okay. So let's give another second derivation, a second derivation that seems more rigorous, although it's actually just the same. Okay, and this second derivation uses what in the old days we called the method of equilibrium partition functions. I think it's now sometimes called thermal effective field theory. You know, we invented this method, this thermal effective field theory 13, 14 years ago to better understand hydrodynamics. Thermal effective field theory is a small part of hydrodynamics. It's equilibrium hydrodynamics. Okay, so hydrodynamics is the master theory. This is a special case. But there is a certain pleasing aspect of it, and I'm going to use it through this talk. So so I'm going to review it. Consider a conformal field theory on the following Lorentzian spacetime. Okay, it's a Lorentzian spacetime that has a time-like killing vector. Okay. Now, every Lorentzian spacetime with a time-like killing vector can be put in this form, where the killing vector is just del t. This is a sort of familiar-looking form. It's a Kaluza-Klein type form, except it's Kaluza-Klein type in time. Okay. Now, because our manifold has a time-like killing vector, it has a conserved charge. Let H denote the generator of time translations. H is a conserved quantity. Since it's a conserved quantity, we can do thermodynamics and compute trace e to the power minus beta h. So trace e to the power minus beta h as a functional of which manifold we're on is going to be the key observable over the next 3-4 slides. Now, I want to compute this trace e to the power minus beta h, and as usual, what I can do is to go to Euclidean space. So I go to Euclidean space by doing the usual weak rotation and compactifying Euclidean time. And so computing trace e to the power minus beta h is the same as computing the partition function of our theory on this Euclidean manifold. Okay. Now, because time is compact, and let's imagine for a moment that beta is small, so temperatures are large, so that this time is compact and small, the effective long-distance theory in 3 dimensions, the effective long-distance theory is 3-dimensional, and is generically massive. Generically massive is something that you can argue from many points of view. Because it's generically massive, it tells us that the partition function, this log z, can be expanded in derivatives of the geometrical data of our compactification. And what's that geometrical data? Well, it's curvatures of the base manifold, field strengths of the Kaluza-Klein gauge field, and derivatives of this factor sigma, this size of the local size of the thermal circle. Okay, and because by dimensional analysis, and also by using while invariance, I'm not emphasizing that at this point, by dimensional analysis, every time you've got a derivative, you have to have a factor of 1 over temperature. Okay, so the most important term at high temperatures is the term with no derivatives. There's a unique such term. It has to go like e to the power minus 3 sigma because of while invariance. Then the next, then there are, if we assume parity invariance for simplicity, the next term's at order t, and it goes like this, and so on. There's a power series expansion. But if we were at high temperatures, we don't care about all these other guys. We just focus on this guy. Now, this e to the power minus 3 sigma, e to the power minus 3 sigma, integrated over this is then the answer for this partition function. Okay. This is a very general analysis, applies to every manifold. But that's not what our interest was. Our interest was the particular manifold S3 times S1, but where the thermal circle included the twist for weighting with respect to angular momenta. Okay, so the thermal circular was identified such that tau went to tau plus beta, and phi 1 prime was also translated as we did that identification. The angle phi 1 prime was translated, and phi 2 prime was also translated. Okay, so this was the identification of S3 times S1 that we wanted to study. So it's S1, it's S3. Now, this is a bit of a pain because, a general formalism of this equilibrium partition function method was set up so that the coordinate tau was identified with all other coordinates held fixed. And we can move to agree with that general formalism. We just do a coordinate change. The coordinate change is we move to the new coordinate phi 1 and phi 2 defined by these guys. With these new coordinates, this identification just becomes tau goes to tau plus beta with phi 1 and phi 2 held fixed. So we're in the framework of the equilibrium partition function method. And the price we pay, though, is that in these new coordinates, the metric looks more complicated. Okay, and this is what we get. We get this complicated looking metric, but note the appearance of these gamma of theta factors, where this more complicated looking metric is of the form of thermal effective field theory or the equilibrium partition function method, where you identify e to the power minus sigma with gamma of theta, the Kaluza-Klein gauge field with this object, and the base manifold metric with this object. Now, it's easy to check that the square root of this base manifold, the square root of the determinant of the base manifold, is the square root of the determinant of round metric on S3 times a factor of gamma. And so when we compute this quantity, the thing that we have to do to compute the partition function, we're supposed to compute e to the power minus 3 sigma, but e to the power minus sigma was gamma, so that's gamma cube. Okay, and then we get an extra factor of gamma from the square root of the metric, so we get gamma to the 4th. And so the log of the partition function is the integral of gamma to the 4. Gamma was, if you remember, a particular function of theta, can be integrated over the S3. It's a simple integral to do, and you find that you get 1 over 1 minus omega 1 squared and 1 minus omega 2 squared. So t to the t cube by 1 minus omega 1 squared to 1 minus omega 2 squared, providing an alternative explanation. It's the same explanation, really, of this high temperature result. Okay, that's all I wanted to say about the high temperature result. That's old story, 20 years old. We're now moving on to new stuff, unless there are quick questions or comments. Great. Okay, so let's move on. Now, still focusing on the S3 times S1 partition function log Z, we turn our attention to the limit omega goes to 1 or nu goes to 0. Remember, our variables nu I, which I sometimes use through this talk, were beta into 1 minus omega 1 is nu 1, beta into 1 minus omega 2 is nu 2. Okay, so nu goes to 0 is same as omega goes to 1. Nu goes to 0 from positive. Okay, so more precisely, we assume that the ratio of the two nu i's, nu 1 and nu 2, are held fixed, and both of them are scaled to 0, such that they're in a manner such that their ratios are held fixed. In our paper, we consider many other limits, many other cases. I'm focusing on just one for this talk. Okay. So a leading order in this limit, this this function gamma of theta plays an important role in this whole story, and it's interesting to see what happens to this function in this funny limit. Now, intuitively, you can see what's going to happen as follows. Gamma of theta is this object. When omega 1 and omega 2 are both set to 1, this object is 1 minus sine square minus cos square, so it's 0. And so it's 1 over 0, so gamma blows up. The question I'm going to ask is, how does gamma blow up? Does it blow up uniformly? Is something else? And it's easy to do a little algebra to check that to leading order in the limit nu 1 and nu 2 goes to 0, gamma squared of theta is this function here. And this is a nice function because nu 1 by nu 2 and nu 2 by nu 1 are held fixed as nu 1, nu 2 goes to 0. We see that gamma squared has an overall blow up times a smooth function of theta. And that's going to be important through my talk in this limit. Okay. Now, the next couple of slides are going to be a bit technical, but I'm sorry, but bear with me. Okay. What I'm going to do is to try to compute or say what I can say about various terms in this thermal effective action. And you remember the various terms in the thermal effective action of the equilibrium partition function were made up of curvatures, field strengths, the sigma field, and their various derivatives. Okay, so what I'm going to do is to compute all these quantities. It turns out to be convenient. In our paper, we adopted the following. tactic, we set up the computation using a Wehrbein field. So we chose three particular, convenient directions. E1 was in the d theta direction where nothing happens. E2 was in the velocity direction, the direction of motion of the fluid. And E3 was orthogonal to both these other directions. And setting up a Wehrbein in these directions, we did some computations of curvatures, and these are our results. Of course, you don't need to remember all these results. The key point here is this. All curvatures turn out to be proportional to no more than gamma square. And every time you see a gamma square, you get really a gamma square. It's not gamma times gamma prime or gamma prime square, something like that, which would have been the same order of largeness. Every gamma square is really a gamma square. Okay? No curvature goes faster than gamma square, and every gamma square is a gamma square. Similarly, no field strength goes faster than gamma square, and every gamma square is a gamma square. Finally, no spin connection term goes faster than gamma, and every factor of gamma is a genuine gamma. Okay? And that's all that you need to know about these computations. Okay? Now, the last thing to realize is this, that we're going to be taking various covariant derivatives, let's say of field strengths or curvatures and so on. Now, covariant derivative is an ordinary derivative times a spin connection. Ordinary derivatives are always order 1. They don't change the degree of divergence, and this follows from the fact that this gamma was a smooth function. So if it had a certain blow up, you don't increase the blow up by taking a derivative. Whereas spin connections do increase the blow up, because then you add this factor of gamma. Okay? So every covariant derivative scales at most like gamma, and at leading order, it has an explicit factor of gamma. Okay, so now we're in business, we can do some counting. Consider Lorentz invariant quantity Q built out of NR Riemann tensors, NF field strengths, and ND covariant derivatives. And these guys could act on either the Riemanns, the field strengths, or sigma, just anything. If you look at the formulae that I just reviewed for you, you will see that this quantity Q can blow up as gamma goes to infinity, as omega goes to 1. But the blow up cannot be faster than gamma to the power 2 times number of Riemann tensors, because each Riemann tensor does not blow up faster than gamma square. Plus, this should have been field strengths. Plus 2 times number of field strengths, because each field strength blows up no faster than gamma square. Plus 1 time number of covariant derivatives. Okay? Just trivial. Now, that I've been working with quantities with lower indices. The total number of lower indices carried by Q is 4nr, because each Riemann carries 4, plus 2nf because each field strength carries 2, plus nd. Consequently, it must be that, to make a Lorentz invariant, Q must have 4nr plus 2nf plus nd by 2 factors of G upper to contract away all indices. Now, the last principle we use is that of Weil invariance. You see, every quantity that appears in this thermal effective action, in this equilibrium partition function, has to be Weil invariant, because we're dealing with the conformal field theory. But it's using conventions in which the metric with lower indices carries Weil weight 2, then of course G inverse carries Weil weight minus 2. E to the power sigma has Weil weight 1. The Riemann has Weil weight 2. And field strengths and covariant derivatives have 0 Weil weight. But you remember that we were looking at a quantity that was made up of NR, Riemann tensors, NF, field strengths, and ND derivatives. Okay? So this quantity, but then we also had to take this quantity and multiply it by a certain number of G upper indices, which had its own Weil weight. Okay? So adding up the explicit Weil weight of the Riemann tensors and the Weil weight of the G inverses, we concluded that the quantity Q we were looking at carried this Weil weight. Now, this is not the right Weil weight for a quantity, so it must have an explicit factor of e to the power minus sigma that will compensate for this Weil weight. And this explicit factor is whatever appears here, okay, times minus 3. The minus 3 kills the Weil transformation of the square root of the determinant. Okay? But remember, the square root of the determinant was square root of the round determinant times an extra factor of gamma. So, and using the relationship between sigma, e to the power sigma and gamma, we find that we get this round determinant times gamma to the power 4 minus this quantity times Q. But now we see something nice. Q itself scales like this. 2nr plus 2nf plus nd. And that's exactly the same quantity that appears here. So these two cancel. Okay, so every term, independent of which order in the derivative expansion, in this thermal partition function, okay, scales at most like gamma to the 4. And every occurrence of gamma to the 4 is genuinely a gamma to the 4. Okay, now this is true in every order in the derivative expansion. So every order temperature in the temperature expansion. And so we have the perfect fluid term, which is minus beta cube, will come with the gamma to the 4. The next term, which is minus beta to the 1, so minus temperature, will come to the gamma to the 4, and so on. Okay, so summing all these things up, we conclude that the log of the partition function goes like h of t divided by 1 minus omega 1 squared to 1 minus omega 2 squared. Okay, and this is one of the principal results of this talk. Now, let's stop to see what this means. Okay. Yeah. What does this mean? Let's suppose omega 1 and omega 2 are scaled to 1. Okay. This gives us the behavior of the partition function in that limit, where h of t is the analog of C prime in the high temperature limit. It's some non-universal function that will differ from a free boson theory to n equals 4 Yang-Mills at lambda equals 3/4. It'll depend on details of the theory. Now, you might at first think you're pretty unimpressed by this result, right? Because we wanted to find a function, a quantity we didn't know, namely the partition function. And I've presented it for you in terms of another quantity I don't know, namely this h of t. And you might think, well, this is just jugglery. But it's better than that, because the thing that I didn't know was a function of 3 variables. And the thing that I don't know on the right-hand side is a function of 1 variable. What I've done here is to give a precise characterization of the nature. We knew on general grounds that the partition function is going to blow up as omega goes to 1. Okay. What I've done here is give a precise characterization of the nature of that blow up. The blow up is always a single pole in any theory as omega goes to 1. And the coefficient of that blow up is an unknown function of temperature. Too bad, it's unknown, but there's a fair amount of information in knowing the nature of the blow up. Okay. Now, in order to convince you that this carries information, let me take this result and Legendre transform it. Okay, so to obtain the entropy as a function of twist J1 and J2 from the Legendre transform. When we undertake that exercise, we find that the Legendre transform takes us to the following charge regime. Takes us to the regime in which J1 and J2 both scale to infinity, and tau scales to infinity, but with J1, J2 ratio of J1 and J2 held fixed. That's of course clear because ratio of nu1 and nu2 is held fixed. But this is the interesting thing. With the ratio tau divided by J1, J2 to the 1/3 held fixed. Okay. What does this mean? Let's imagine J1 and J2 were the same. So this is that it takes you to it's a large J limit where J is becoming large. Tau is also becoming, twist is also becoming large, but slower than J because it scales like J to the 2/3. Okay? The generic high temperature limit is one in which tau and J both become large in the same way. This is a different limit. J is large, tau is large, but J is larger than tau. Tau goes like J to the 2/3. Of tau divided by J1, J2 to the 1/3. This function is non-universal. Okay, it's non-universal. It's in some vague sense like a Legendre transform of that h of t, the non-universal function of temperature that we talked about before. Okay, good. Clearly, the scaling form carries energy, carries information, and in order to understand what information it carries or what this reminds you of, if you stared at this thing, you'll realize you've seen something like this before. Consider a theory in which which carries energy and volume, and both energy and volume are both large, but the ratio is held fixed. Now, all reasonable theories, quantum field theories, are extensive. So the entropy of this theory will behave like volume times an unknown function of energy by volume, energy density. And this is exactly what we're seeing in this formula. This formula tells us that the entropy is behaving extensively with a new emergent notion of extensivity, with angular momentum playing the role that volume originally played, and twist playing the role that energy played in the analogy that I talked to you about before. Okay, more precisely, the volume is J1, J2 to the 1/3. Okay, last quick comment. Okay, fine. Now, this is the final formula, this guy and this guy are global formulae. It's just for grand thermodynamic objects, partition function, entropy. However, remember, we got it much more locally. We got the answer by integrating the local free energy density of the thing. And so we knew the local behavior of everything, not just the grand global behavior. So, you might expect that we know more than these global quantities. We can make predictions for local quantities. And in our paper, we predicted, based on various considerations, that the 1-point function of the stress tensor in this partition function would also be semi-universal, also be governed by the same data, the same unknown data that governed by the partition function, and take this hydrodynamical form. We didn't have a very clear proof of this in our paper, but we've since found one, and we will publish it soon. Okay, now, just before I move on to the next part, this is like a note added in proof. Okay, a few days ago, Zohar sent me a copy of a very interesting follow-up paper that follows up on the work that I've just described to you in this talk. I saw on your schedule that Zohar will be giving a thermal seminar in the next couple of weeks. In this slide and next, I give a sneak preview of these results, which I presume he'll talk about. But I'll do it in the language that I've used in my talks. This might help people who attend both my talk and his relate the two works. Look, you see that our main result, one of our principal results was that the free energy density scaled like gamma to the 4. And you remember that the way it happened was that there was a term proportional to gamma to the A that was came from curvatures. A term proportional to gamma to the 3 minus A that came from the sigma scaling determined by Weil invariance. And a term proportional to gamma that came from scaling of the volume of the base manifold. And putting them together, we got gamma to the 4. Now, we worked in this completely Weil invariant. Instead of taking this Weil invariant approach, Zohar and friends, in their upcoming paper, choose to fix Weil gauge. They choose to work in a very beautiful choice of Weil frame determined by the condition sigma equals 0. Now, if you work in this sigma equals 0 frame, this factor gamma to the 3 minus A, which came from the explicit factors of sigma, of course, is missing. And because this is missing, and because this final factor of gamma to the 4 is Weil invariant, so it will be the same in every Weil frame, this curvature factor can also not depend on A. When you do the computation, you find it scales like gamma to the plus 0. Okay? And in their frame, every factor comes from the volume of the base manifold, which in their Weil frames itself scales like gamma to the 4. So in this very beautiful choice of Weil frame, the power counting I gave you is much easier. Curvature scale like 0. E to the power sigma factor scale like 0. Volume scales like gamma to the 4. The fact that curvature scales like 0 tells you that in this choice of Weil frame, the base manifold, and in fact the whole fibration manifold, is a smooth manifold. And so this gamma to the 4 was just the volume of the base manifold. As I've described above, that volume is proportional to 1 minus omega 1 squared, 1 minus omega 2 squared, which you can easily check is scales like J1, J2 to the 2/3. Oh, sorry, 1/3. This should have been 1/3. J1, J2 to the 1/3. Okay. This should also have been 1/3. Okay. And why I've written it twice, I cannot say. But the fact that the curvatures vanish tell you that as I said, in the Weil frame, everything is smooth. And the fact that the volume of the base manifold is J1, J2 to the 1/3 gives you a completely satisfactory explanation of this semi-universal behavior, the behavior we call semi-universal, this volume times extensive scaling, because it really just is extensivity in this frame, extensivity of the base manifold. It's a really beautiful observation. And as I said, I think you will hear more about it in upcoming talks. Okay, but let's move on. Now, in the rest of this talk, I think I have something like 15 minutes to go. In the rest of this talk, I will check the central prediction of our paper in two examples. First, I will work with, an example that every string theorist naturally turns to when wanting to check anything, namely n equals 4 Yang-Mills theorem. And then I will work at in n equals 4 theory, Yang-Mills theory, it's strong coupling. And I will use ADS CFT, the gravity dual description, to make predictions and check to see if it's working. The other limit we will look at is, you can say, quote unquote, n equals strong Yang-Mills at 4 Yang-Mills at weak coupling, but more precisely, we didn't bother to check the fermions and the gauge fields. We just did the scalars at weak coupling to check how things work. Okay. Let's first start with strong coupling. Okay. What we want to do is to ask, what does ADS CFT tell us about how the entropy of n equals 4 Yang-Mills theory scales as a function of J1, J2, and tau in the limit J1 goes to infinity, J2 goes to infinity, tau goes to infinity, tau divided by J1, J2 to the 1/3 held fixed. Okay. Now look, we're interested in this theory of very large values of all charges. There is this usual expectation in ADS CFT that if you want very high values of charges, the thermal ensemble will be dominated by a black hole at the back. Now, black holes come in various varieties. The black holes that are 10-dimensional black holes, those that are localized on the S5. There are black holes that are 5-dimensional black holes, those that are smeared on the S5. The general rule is that when you go to very large charges, smeared black holes win over localized black holes, and that will be the case in our situation. Okay, so for a part of our phase diagram, as I will describe to you in a minute, our phase diagram will be dominated by a Kerr ADS black hole, which is, from the point of view of 10 dimensions, a black hole that is smeared on the S5. Okay, so I'm going to take 2 or 3 minutes to tell you a little bit about these black holes. Okay, anyone who's, these Kerr ADS black holes, ADS5, they're written down long ago. And when you look at the classic paper that looks at their geometry, those of you who've done such things know that this classic paper gives you a 3-parameter set of Kerr ADS black holes. 3 parameters, why? Because there's 3 parameters, J1, J2, and energy, or omega 1, omega 2, and T. But the parameters used in these papers are called A, B, and M. Roughly, A is, encodes the information of omega 1, B encodes the information of omega 2, and M encodes the information of the mass, or the energy of the black hole. Okay. Now, logically speaking, I should present all formulae I'm going to you as functions of A, B, and M. But this equation here gives us the location of the outermost event horizon. The outermost event horizon of the black hole as a function of A, B, and M, and it's unfortunately a cubic equation in A, B, and M, and cubic equations are sort of unpleasant. So the way I'm going to parameterize these solutions are parameterizing them by A, B, and R plus, and I'll treat M as a derived quantity. It's as good a parameterization as any other. Okay, so my black holes are parameterized by 3 quantities, A, B, and R plus, and then I can just solve for M. That's a linear equation, so that's easy. Now, in terms of these A, B, and R plus, one can compute all the charges of these black hole solutions, and one finds that J1 by n squared is this, J2 by n squared is this, tau by n squared is this, entropy by n squared is this, and what is this? What are delta A and delta B? Well, in this old Kerr ADS paper, the authors will tell you that A cannot be made larger than 1, otherwise you develop closed time-like curves. Okay, and so we scale to the end of that limit. So we set A is equal to 1 minus delta A and B is 1 minus delta B, and work in leading order in delta A and delta B with, you will see, ratio of delta A and delta B fixed. And in that limit, the complicated thermodynamic formulae of this paper simplifies to these simple formulae. Now, what's the point of these formulae? The point is this. You take this formula for S and divide by n squared J1, JB to the 1/3, and you find the simple function of R plus. You take this formula for tau and divide by JB to the 1/3, and this factor of n square, and you find this other relatively simple function of R plus. Okay, and you take J by JB and you find it's delta B by delta A. So, okay. So now we're interested in the limit J goes to infinity, JB goes to infinity, ratio held fixed. So we must take delta B by delta A fixed. Delta A and delta B going to 0 takes J and JB to infinity. And we were interested in the limit that the tau divided by j by jb to the 1/3 was held fixed. And so that tells us we should keep r plus fixed. So we should take delta A to 0, delta B to 0, R plus held fixed, ratio of delta A, delta B to take that to hold that fixed. And this is the limit we want to study. Great. So now what we can do is to take this quantity and solve for R plus as a function of this tau divided by JB to the 1/3, plug that solution back in here, and that gives us the formula for this entropy as this effective volume times some function of tau divided by JB to the 1/3. Because there's n square, but you should think of our charges being the largest parameter in the problem. So n square is just some decoration from this point of view. Okay. And so that tells us that Kerr-ADS black holes obey semi-universal scaling from the microcanonical point of view. And it's sort of pretty cool. These solutions, many people, certainly I myself, have studied for over decades. You need the right eyes to see that it had the semi-universal behavior, and you found those eyes to see it once you realized that it had to be the case. Okay, so far I've worked in the microcanonical ensemble. Now let's move to the canonical ensemble. Okay, once again you can use the classic thermodynamic formulae in classic papers, and you set the omegas of these black holes to be 1 minus delta omega 1, 1 minus delta omega 2. And you find the following formulae to leading order in delta A and delta B for canonical formulae. That as delta A goes to 0, delta omega goes to 0. That also happens. Okay? T is fixed if R plus is held fixed. And log Z is given by this formula. So there are two things I want you to notice about these formulae. Okay. The first thing to notice is the kind of thing we were talking about before. If you remember, our semi-universal scaling limit from the point of view of the canonical ensemble was holding T fixed and taking omega 1 to 1 and omega 2 to 1. Okay. So as we concluded before, holding T fixed is the same as holding R plus fixed. Okay. And we can use this to solve for R plus in terms of T. Okay. Once we have that, we have this h of r plus, which is some explicit function of r plus. We plug the solution back in and you find this h of t function that appeared in our general analysis of semi-universality, which was some abstract function depending on dynamical details at n equals 4 Yang-mills at high temperature. And you'll see why at high temperature in a minute. That h of t function is this very explicit quantity. Look at how beautiful and simple and small it is. You can take it and expand it in a power series expansion in temperature. It's convergent. Anything you want, you can do. Okay, so n equals 4 Yang-mills at strong coupling. We've computed this h of t function. Very beautiful function. Now, that's the first thing. The second thing I want to say is something more interesting. Look what happened. There's a special value of r plus, namely r plus equals 1. And when r plus becomes less than 1, two things happen. First, this delta omega A becomes negative. And second, this h of r plus also becomes negative. Okay, now what does it mean that delta omega A becomes negative? Remember, omega was 1 minus delta omega. If delta omega is negative, then omega is greater than 1. And you remember we spent a lot of time arguing at the beginning of this talk, that should not ever be allowed to be. Okay, so delta omega A is greater than a negative is an illegal black hole solution. Now, the fact that black hole solutions area as 5 times S5 sometimes classically do have omega greater than 1 was something that was discovered 2004. And what it meant was clarified in a paper we wrote 2 or 3 years ago on gray galaxies. It means, of course, and this people knew before, that the black hole was unstable. But what we did was to find the endpoint of this instability. A gray galaxy, which is a black hole in the center of ADS times a disk of whirling stuff around it. Okay. And the point at which the black hole became unstable was the point at which delta omega A went from positive to negative. So R plus equals 1, which notice happens at T equals 1 by 2 pi, if you put, 1 by 1. R plus equals 1 or beta equals 2 pi, T equals 1 by 2 pi, is the instability bound for these black holes. So at higher temperatures than 1 by 2 pi, n equals 4 Yang-mills is in this phase and has this beautiful formula. At lower temperatures, something else happens. The second thing you remember I asked you to notice is that R plus went from positive, that this H went from positive to negative as R plus went from greater than 1 to less than 1. Now, what does it mean that if H goes from positive to negative? H being positive is a Hawking-Page stable phase. H being negative is a Hawking-Page unstable phase. So we see here that R plus equals 1 in this particular semi-universal limit. Okay, R plus equals 1 is both the superradiant instability that leads to the formation of gray galaxies, as well as the Hawking-Page transition. This is sort of interesting. In a genetic study of gray galaxies, without taking this this strong large angular momentum limit, we found that these Hawking-Page and superradiant instabilities were separated. If you lower temperature first, you hit Hawking-Page, then you hit the superradiant. In the semi-universal limit, these two merge together. This is a result of extensivity, as I will tell you about in a little more time. Okay. Now, so as we've said, this can be the right answer for beta less than 1 by 2 pi, beta less than 2 pi, temperature greater than 1 by 2 pi. But what happens at lower energies? Okay. At lower energies, we get these gray galaxies. And we've worked out in our paper the gray galaxy solutions in the semi-universal scaling limit. They turn out to be very simple and have a very simple entropy formula. The entropy formula is just 2 pi. It's hagedorn-like, but with a order 1 hagedorn temperature. 2 pi times tau. Now, there's this lovely identity of mathematics that tells you that tau is equal to J1, J2 to the 1/3 times tau divided by J1, J2 to the 1/3. So that tells you that this simple formula 2 pi times tau indeed is of the semi-universal scaling form that we predicted in our paper. Okay, notice that the phase transition of the gray galaxy in the semi-universal limit equals 1 by 2 pi. The same as the Hawking-Page phase transition of a 2D CFT, of a large N2D CFT, for the special point for modular invariance. This is probably not a coincidence. I'd like to understand why, but I don't know the answer yet. Okay. Okay. And actually, when you do the analysis of this paper, when we do analysis in a little more detail, we find that there's actually a third phase. When I went back to the canonical ensemble, there was a phase transition in tau of order n to the 2/3. So tau greater than some number times n to the 2/3, we had the black hole phase. One, there was a gray galaxy phase. And the second phase transition at scale tau divided by J1, J2 to the 1/3. Everything's a function only of this scaled parameter. It's tau divided by J1, J2 to the 1/3 of order n to the 2/3. And there's a second phase transition when tau divided by J1, J2 to the 1/3 is lowered below some order 1 number. We know the numbers. Okay. I'm just saying some order 1 number. And then in this lower temperature phase, the system is just dominated by a gas, just thermal gas and ADS. So we have 3 phases in the system. High temperature black hole phase, medium temperature gray galaxy phase, low temperature gas phase. And in all 3 phases, up to one caveat I will tell you about in a bit, we are able to compute the answers. And in all 3 phases, semi-universality works. Okay. Now, one thing I wanted to say here. The phase diagram I described to you in this subsection, one thing I didn't say is that all through this phase diagram, while the gray galaxy phase extends over a whole range of twists, all through its existence, this gray galaxy phase is at a particular temperature, namely 1 by 2 pi. So if you work in canonical ensemble, you see the 3 phases. At temperature larger than 1 by 2 pi, black holes. Temperature equals 1 by 2 pi, you have gray galaxy. Temperature less than 1 by 2 pi, you have the gas. Now, the phase diagram I described in the subsection has a close similarity with a very familiar physical system, namely that of boiling water. Okay, the fixed number of water molecules N is analogous to the fixed angular momentum of our system. The internal energy U of the water is analogous to the twist of the N equals 4 system. And the extensivity of the water, the fact that S water, the entropy of water, is N times G of U by N, mirrors the extensivity of the N equals 4 of this, the extensivity that we've discovered in the semi-universal limit. Within this analogy, the black hole phase is analogous to steam. Now, remember, when you take steam and you cool it, you keep cooling steam until you hit 100 degrees Celsius. And then for a while you cool and the temperature doesn't change. Just more and more the steam is changing into water. And you've got a half water, half steam phase. Okay? And that half water, half steam phase is analogous in the semi-universal limit to the gray galaxy phase. Okay? And then you finish cooling enough so that all the steam has become water, and then you cool more, and then the water goes down below 100 degrees Celsius and becomes just all water. In the same way in our system, you finish cooling enough, the gray galaxy phase becomes all gas, and then it starts cooling down further. Okay, so this close analogy to this, to the phase diagram of boiling water. In this analogy, in the semi-universal limit, gray galaxies are like a half water, half steam phase. And the fact that it all happens at one temperature becomes so analogous to boiling water. The thing that's responsible for that is the effective extensivity of this large J limit, which is a really cool thing. It's extensivity determined by angular momentum, not by apparently a large volume. Okay, now I am running out of time. I'm running out of time, so let me just say this very quickly. In our analysis of n equals 4 Yang-Mills, the black hole phase we analyzed just completely. Okay, we analyzed the gray galaxy phase and the gas phase with certain approximations, and these approximations worked. Okay, these approximations worked when J, the angular momentum, the scale associated with the angular momentum were much, much less than n to the power 6. Okay, I won't go through. Yeah, it's this J much, much less than n to the power 6. So in the strict large J limit, if you hold n fixed and take J to infinity, we don't really quantitatively have control over the gray galaxy and the gas phases. Up to J equals n to the power 6 we do. This is a new and interesting scale. I've never in my life seen something scale like n to the 6 before. Something interesting going on here that I think needs to be understood better. Okay, one or two quick last comments and then I'll stop. Okay, one of the things we do in our paper is to show that this semi-universal scaling also works in the light cone limit. Now, what do I mean by that? As you guys know, previous studies of the large J limit have been, abundant in the study of conformal field theory. This is the so-called light cone limit, where people look at the limit J goes to infinity at fixed tau. Okay, in this limit, the theory becomes free. It's like a Fock space of free stuff. And if you look at a Fock space of free stuff, effectively up to some post-Fermi business that changes nothing, I'm saying, what you get, your partition function is the exponential of a single particle partition, the one particle partition function, where the particles are the things that are making up the Fock space. Okay, now these particle partition functions are conformal field theory characters. And if you think about it for a minute, you will convince yourself that conformal field theory characters have this factor of 1 over 1 minus omega 1 squared times 1 over 1 minus omega 2 squared that we see in that we've seen in this semi-universal formula. So when you exponentiate this and then take log, you see in this Fock space way of thinking also, you get this factor of 1 over 1 minus omega squared 1 squared and omega 1 minus omega 2 squared. So you might ask, what is the relationship of this easy to understand Fock space semi-universality and the universality we found, the new semi-universality we found in our paper? And the answer to that turns out to be sort of interesting. Okay, look, in our paper, what we did was, when does this Fock space sort of formula become nearly correct? I'll be done in 2 minutes, okay? When does this Fock space formula become nearly correct? Well, in the gas phase, it becomes nearly correct, provided that gas interactions can be ignored. In the black hole phase, we're totally far from a Fock space, right? A black hole is not a Fock space of things at the bulk, it's just a thing. Okay, but in the gas phase, you're nearly in a Fock space, provided that the interaction between gas particles can be ignored. I told you that interaction between gas particles could be ignored in certain regime, when J to the 6th was much, much smaller than n squared. And that translates into the following statement. Yeah, the interaction between gas particles can be ignored if gamma squared by n squared is much, much less than 1. Gamma squared by n squared times, if you go to low temperatures, this factor of x is important, where x is e to the power minus beta times the twist gap of modes in the bulk. Okay. Now, I want to hold n fixed and take gamma to infinity. So if I just hold n fixed, I hold x fixed and I take gamma to infinity. So x fixed is like fixed temperature. I will never have this much less than 1. One way of making this more controlled is to take the following limit. Take the limit, nu goes to infinity, or gamma goes to infinity. Sorry, nu goes to 0, which is the same as gamma goes to infinity. Okay, x goes to 0. such that x times gamma squared is held fixed. Gamma squared is like 1 over nu. So I've written it as x by nu held fixed. Okay, and I've called this fixed quantity whatever it is else n square alpha. Now, this is a new scaling limit, one that has not been considered in the light cone bootstrap and one that has not been considered in our paper. Now, how do we approach n's? If we take alpha to infinity, you see, what we're doing is taking a very low temperature limit here. Okay, if we take alpha to infinity, it's so low temperature that it's temperature that's taken low as you scale. If we take alpha to infinity, we approach zero temperature of our new semi-universal scaling limit. On the other hand, if you take alpha to 0, you approach non-interaction, because alpha now controls the interaction in the bulk, and then you approach the light cone bootstrap. So what we realize is that there is a new scaling regime that lies in between our semi-universal scaling regime and the Fox-based scaling regime, and the light cone bootstrap. And this new thing should be explored. There's a wealth of physics to find here. Okay, I think I don't have the time for this free stuff, so I will just end. Okay. So there are many open questions. My first open question from a week ago was, can we find a proof of our central result without resorting to a power expansion in beta? But this new Stony Brook paper has gone at least a long way in doing that. So that's you can make a tick. Can we find new non-trivial checks of a conjecture, for instance, Mattachern-Simon's theory in D equals 3? What about this alpha scaling limit that interpolates between light cone bootstrap and our limit? The thing I'm really interested in is this. In the study of the high temperature limit, equilibrium was the tip of the iceberg. What was really interesting was hydrodynamics. That led to the fluid gravity correspondence. I wonder if there is something analogous here, a new kind of fluid dynamics that governs physics in this regime. There are other questions you can ask. I'll stop here. Sorry for